Namaste and welcome to Apna Gurukul Maths. Today we are going to discuss about Euclid's geometry. This is the fifth chapter of class 9th NCERT textbook. And Euclid's geometry, once we see this chapter, it looks a very easy chapter. And sometimes you might think that everything discussed in this chapter is pretty obvious. Then what's the need to study this? Okay. So if you have all of these questions in your mind, please watch this video because I will show you why this chapter is very much important and how obviously this chapter does not have much weightage for your examination point of view, but yes, it gives you a very good perspective of how mathematics is developed, especially in this case how geometry, how the branch of mathematics called geometry is developed. Okay, let's get into the chapter. Let's try to understand first the meaning of what is geometry. Okay, geometry is made up of, the word geometry is made up of two words. The first is geo and the metry. So geo means earth and metry has been taken from a Greek word that is called metrion, which means to measure. The measurement of earth gives you the word geometry. Okay, so that is how the word is taken. Now there's a very famous saying, geometry is an abstract model of the world in which we live in. Right? So now you might be thinking, why was this geometry developed? Now, this geometry is a concept which has been developed by looking in and around us, whatever things we had during those days in which it was developed around 400 to 500 BCE before Christ era, before Common Era, I'm sorry. So it was developed during that time. Now, whatever in nature we have, we try to observe and put it in the form of a branch of mathematics. Now, why was it needed? Why do we need to observe whatever is there in our surroundings? All those things we will cover in a while. Yeah. Now, geometry is widely studied. Now, it is been known that it's been widely studied throughout various civilizations, be it India, China, Egypt, and so on, all the other great and ancient civilizations. Everywhere the geometry was studied. But why was geometry needed? Okay, so first of all, the need of geometry came for need of measuring land. When the people started to give that this land is mine, this land is belongs to somebody else, and all those some definitions when it started to be given, then we need to measure land. There need to be a step, or I would rather there need to be a procedure which gives us how to measure the land. If there is no procedure of measuring the land, how are we supposed to understand? Means that's common sense, right? If there's no proper measurement technique, then anybody will measure anything, right? Every day it keeps on changing. So that standardization was needed while measuring the land, and that's how the need of geometry started to come. Then for solving some practical problems and amazing and for creating something amazing, for these two things geometry was needed. For example, in those days flooding was a very common, still there at places the flooding is very common. Now once they mark the land and flooding, it all flooded out. After the after season has gone, the water has been dried up, how to identify which land was mine and theirs? So this was a serious problem. So during that times, the geometry, the basic geometry started to develop. And then came the amazing creation, Indus Valley civilization, which is known that it's 3000 before Common Era. It is so old civilization. And while archaeologists found several Mohenjo-daro civilization, Harappan civilization, so many developed and geometrically almost perfect shapes and buildings. So during those times, geometry was used to create those beautiful cities and civilizations. Ancient temples of India, we will we will to take a deep look at this ancient temples of India. When you visit throughout the India, there are lots and lots of different temples which has used extensively the geometry, right? It was not possible to construct those temples without a proper knowledge of geometry. That precise knowledge of geometry was there in the ancient Indian civilizations. Now, once again, there is around 800 BCE to 500 BCE. There was a Indian literature which was called as Sulabha Sutras. Now, sutras means formulas. Sulabha is related to geometry. Okay, Sulabha Sutras. Now, it was a manual for geometric constructions. So it all began with the construction of Vedis. Now, the Sulabha Sutras were developed on the basis of, in those days, Vedis are fireplaces where yagnas are done, very, very big yagnas are done. And that's how these construction of Vedis started, and it related to geometry. Now, how are they related? We will discuss it for 2 to 3 minutes. Now, in those days, different types of Vedis were created for worshipping, and all the Vedis had a different significance altogether. One of the very, very famous Vedi was Sri Yantra. Now, if we take a deeper look at Sri Yantra looks something like this. As you can see, there are 9 interwoven triangles over here. As you can see in the picture, there are different types of polygons also interrelated over here. You can see there are triangles over here. As you can see, there are lots of triangles. So when you study this shape very, very carefully, it shows you that there are 9 interwoven triangles, and because of these 9 interwoven triangles, there are 43 subsidiary triangles weaved in it. So that's how great precision of geometry they had of polygons. And as you can see, there are different polygons also involved. Now, this picture has been taken from adrikpanchang.com. This is not the picture made by me, but yes, so this was one of the, in ancient India, this geometric construction was used. Now, these accurate geometric methods were used in construction across civilization, but principles behind them were never discussed. Why, when you construct triangles, they have 3 sides? Why are they so like a triangle is considered to be the hardest shape? Why is that so? Means for every there was no reasoning for that constructions. So when the reasoning behind those constructions it hit into the mind of human beings, then there was a development of proving all these constructions, proving all these rules being used in this precise constructions of ancient civilizations. So as the civilizations grew, reasoning behind all the constructions was a major topic of discussion. So we started looking for proofs, and in Greek civilization, there was a Greek mathematician who was known as Thales. He was credited for the first proof. He proved several theorems related to circles. We are not going to discuss what he proved, but yes, he is credited to give the first proof in mathematics. And then came one of his student, Euclid, one of, I won't say students, one of his disciples in those days, that was a good word. So one of his disciples, he collected all the possible information of those days related to geometry and put it in the form of a book which is called as Elements. And in that element books, he gave a lot of definitions, a lot of principles, a lot of axioms and postulates, a lot of theorems, which gives us a very, very good idea about what geometry is. And in that book itself, there's a very, very important sentence. Geometry is abstract model of the world which we live in. Yes, so that is a very, very meaningful and powerful statement. Now, it's just whatever we have observed in the world, we have put it in the form of a concept. Why do we need that concept? Let's discuss that for a while. Now, if we don't know the reasoning behind anything, it is very difficult to teach that. Now, suppose in ancient civilizations, the geometry was used very precisely, but why is it not that precise at the moment? because the principles were not given. The textbooks, because of several invasions and all those things, it was burned. Right? So since the principles were not taught, that method was lost. And that is why the principles are important. And that is why, after reading some things about polygons, quadrilaterals, we have already studied in some things about this in class 7th and 8th. In ninth, once we are going towards pure mathematics, it is important for us to understand what are the principles involved, what are whatever we have right now, how it has developed. And that is why it becomes a little bit important. Now, I'll take an example of how it is an abstract model of the world we live in. Now, whatever solid shapes we have, let's try to take only the shapes which has straight lines, because Euclidean geometry only talks about the straight line. We will discuss about this towards the end of this video. Now, if you have all the solid shapes, suppose you are whatever room you are living in the room which you are living in, the boundaries of this solid shape, when you see, look at that, the thickness we ignore, so that is called as a surface. Yes, and we can study various properties about surface when we bring that on a piece of paper, right? So that is how, that's a world we live in. Abstract model, we have brought a surface. Yes. Now the surface, as you see the boundary of the surface, they are called as straight lines. Or if you are looking a curved object, a curved line. Yes. Now where does that line ends? That line ends on a point. As you can see, the pretty much corner of your wall. Yes, that is just a point. So it's a very good example to visualize whatever world we have right now, whatever room we are sitting in, we have put that in the piece of a paper so that we can study it in detail, we can study its properties. And if we understand the properties, it's easier for us to build and construct different buildings, different monuments, to create. Building is a very light word. We can create something beautiful architecturally. Yes, so these principles helps us in develop that. Now, I have given enough importance of this particular topic, what we are discussing in. So before we move on to what really those axioms and postulates are, let's try to understand what are axioms and postulates. So axioms and postulates are nothing but they are obvious truths. Now, when we try to observe different things in our nature, some things need not be proved. They look very obvious according to our observations. And that is what happens with mathematics as well. So those things are called as obvious truth. When we have obvious truth, we have categorized that into two ways, that is axioms. So axioms are used in general mathematics. Wherever you go in mathematics, the axioms can be used. Okay. Now the postulates are only limited to geometry, and that is why we will focus more on postulate in this particular chapter, because we are obviously discussing Euclid's geometry. Now let's quickly go through the axioms first, and then we will move to the postulate. So the axioms, now they will look pretty obvious because they are obvious truths, right? So they should look obvious, but once it was not given as a rule or an axiom it per se, it was very difficult for the people to understand this. And that is why these axioms were given, and that is why we need to study this so that we can understand the importance of this. Yes. So things which are equal to the same things are equal to one another. What's the meaning of that? So, suppose I say A is equals to B, and also A is equals to C. That is what, right? Things which are equal to the same thing. That means B and C are both equal to A. This implies B is also equal to C. Now B is a situation over here. It's not. It need not be an alphabet. I'm representing a situation with the help of A, B, and C. Right. So A, if the situation A is equals to B and situation A is equals to C, that implies situation B equals to situation C. Now, the second axiom. If equals are added to equals, the wholes are also equal. I'm sorry, the spelling. The wholes are also equal. For example, if you can see it over here as well, okay? If equals are added, suppose A equals B and C equals D. If you add A plus C, then it will be equal to B plus D. Again, I'm talking about the situation. Okay, you can take this with numbers. 5 equals 5, right? 6 equals 6. The 6 is equal 6. If you add both of them, 11 equals 11. That's all, right? It's very, very easy to understand. If equals are subtracted from equals, the remainders are equals. Suppose same 5 and 6. If you subtract both of them, 6 minus 5 is 1. 6 minus 5 is 1. Obviously, they are equal. Yeah, you can understand with the help of situation as well. Now, things which coincide with one another are equal to one another. For example, if we have a line, and if another line, I have the second line of similar size, if I bring them one upon each other and they overlap or coincide completely, this is known as that implies that they will be equal. Now, you might be thinking, why is it used each other or one another? For that, I will try to explain you with two textbooks which I have right now, two notebooks I would rather say. Now, as you can see, this is our maths textbook, and this is from one diary kind of thing. Now, one another, why equal to one another is important. I'm explaining you that. Now, if I keep this diary on top of this and show you like this, you can say that the textbook is overlapping the diary. But when I show you like this, is the diary overlapping the textbook? No, right? So this is not a condition where the things coincide with one another. The book is coinciding the diary, but the diary is not. In that situation, they won't be equal. But if we could find a situation where both are overlapping each other or coinciding each other, they will be equal. I hope that is clear. Yeah. With this, we'll move to the next axiom. I'm sorry, these are 5, 6, and 7. Yes. So the whole is greater than the part. Now, suppose when do we use wholes and gray? Suppose I write 2 by 7. So this is a part of the whole, right? So 7 parts out of that we are considering 7 in whole, and 2 parts we are considering. So obviously 7 will be greater. That is very, very simple to understand. The wholes will obviously be greater than the part. Yeah. Now things which are double of the same thing are equal to one another. For example, I will again take 6 equals 6. If I make the double of 6, that becomes 12 equals 12. That's all. Suppose I write A equals B. Yeah, A equals B. If I make a double of 2, that will also be equal to 2B because A equals B. So that gives us the sixth axiom. The seventh axiom being uh, A equals B. I'm again talking about situation. It could be also numbers as well. Now, A divided by B will also be equal to B divided by 2. A divided by 2. I'm sorry. I guess I told A divided by B. A divided by 2 will also be equal to B divided by 2. And that is what the seventh axiom tells us. I hope this makes sense. And Euclid's axioms are clear. Now, my dear students, do not think that you have to memorize these axioms. No, not at all. These are just for basic understanding, and we take help of these axioms for a bigger purpose. I will explain you that bigger purpose as we proceed further in the video. Now comes Euclid 5 postulate. I'm sure you are very much clear with what is the difference between axioms and postulates. Obviously, they are universal truths, as well as there is one more thing. Axioms and postulates need not have a proof. That is why they are obvious proof. We need not give a proof that why over here, as we discussed, the whole is greater than the part or any of the axiom. Yes, we need not have a proof, structured proof for that. It is accepted as a truth in mathematics, and that's why it is called as axiom. Now, in mathematics, you always try to observe whatever we have studied so far, there are few assumptions every time. Those are called as axioms. We build on that axiom. One axiom we have observed from the surrounding, we have accepted as it is. Now all the mathematics is built on that obvious truth. If you can take example of numbers as well. Why 2 comes after 1? Do you have a proof for that? Do you have a reasoning for that? No, right? We have taken an obvious truth that after 1 there'll be 2, after 2 there'll be 3, and all the further numbers. Yep. So that is why it is taken like this. Now let's understand Euclid's postulate. It's only related to geometry. A straight line may be drawn from any one point to any other point. Suppose you have 2 points. You can suppose you have any 2 points. Every time you can draw a line connecting these 2 points. That is what the first postulate says. The second postulate says a terminated line can be produced indefinitely. Suppose we have a line AB, as you can see in the diagram, AB. Now, it can be produced indefinitely. Means, suppose the B is the end point of the line segment, right? We write it as line segment. If we start extending it towards B, it can keep on going, right? If we start extending it, that is what it is saying. In both sides, it can be extended indefinitely. What is the meaning of indefinitely? We cannot define how long it can go. Great. Now, coming to the third one, a circle can be drawn with any center and any radius. Now, what is the definition of circle? A circle is a collection of all the points which are equidistant from a fixed point. Now, in this case, fixed point is this. Now, we mark all the points which are equidistant. This is 1 point, second point, third point, and all the other points if we mark them. And obviously, there'll be infinitely many points. So, when you connect all those points, you get a circle, and that is how the circle is defined. And hence this axiom, a circle can be drawn with any center and any radius. It is not compulsory that this is the only possible circle, right? I can take this as center. I can take any radius and make a circle. I can take the center. I can make any radius and make a circle. This looks a little bit bigger, but yes, you can. I'm just trying to explain you. I hope you have understood. Now, fourth one, it might seem like a joke, but yes, all right angles are equal to one another. If you draw an angle which has a measurement of 90 degree, no matter what size you make this one, and suppose I made this 90 degree, okay, the rays, angles is obviously made from rays, right? So these rays might be different, but the angle 90 degree will remain 90 degree no matter what. I hope that makes a lot of sense too. Now, this one is the fourth postulate. The fifth postulate is one of the most important postulate. Please pay a close attention. Fifth postulate says if a straight line falling on two straight lines makes the interior angles on the same side it taken together less than two right angles, then the two straight lines, if produced indefinitely, meet on that side on which the sum of angles is less than two right angles. Now, this looks very clumsy. Yes, let's try to understand it with the figure and with a few measurements. I hope you will enjoy this. Now, we have two lines AB and CD, and we have one line, I will call it as line L, passing through this and meeting at two distinct points, that is P and Q. So this L is called as transversal. Okay, now whenever we have talked about transversal, always it comes in our mind that it's only for parallel lines. No, my dear student, any line which passes two other lines at distinct places. What is meant by distinct places is, suppose I have lines like this. Okay, these are two different lines, and there is a third line which is passing through this. But here, as you can see, it is intersecting both the lines, but it is intersecting both the lines at the same point. There's no two different points. That is meant by distinct. Distinct means it should be different points. Okay, that is what is seen over here, P and Q. Now what I'll do is, I will bring the protractor. Now here is our protractor. Now what will I do is I will try to measure the angle. Now let me clarify first of all. Now what are interior angles? These are interior angle. I'll name it as angle 1 and angle 2. Angle 2 and angle 1 are interior angles, and angle 3, angle 4 are also interior angles. Yes. So we will try to measure these interior angles. I hope you are very clear with how do we measure with protractor. Over here, as you can see, we have kept the midpoint on the vertex, and then we have made the baseline coinciding each other, and this angle 2 is 35 degrees. Yes, so we will quickly take a note of this. Angle 2, what we have is 35 degrees. Yes, now till then you can keep thinking, angle 1 and 2, are they on the same side of transversal? I hope you have got the answer, but still I would ask you to think. Now, in this case, we will take the outer angles and it goes to 135. So, angle 1 is 135 degrees. Yes. Now, let's try to measure angle 3 and angle 4 as well. Angle 3 is, now you can simply, we know that it's a straight line, so it will form a linear pair. So since the angle 1 is 135, angle 3 should be quickly 45 degrees, because 180 minus 135, 180 minus 135, if you do, you get 5, 7 minus 3 is 4. So this becomes 45 degrees. Angle 4 will be equal to, now angle 2 is 35 degrees. So 180 minus 35 gives you 145 degrees. Yes, I hope that is very clear. Now, 1 and 2 are on the same side of transverse, angle 1 and 2, right? So add angle 1 and 2. So that is 35 plus 135. That gives you 170. Yes or no? Yeah. Now, try to add angle 3 and 4, 45 and 145. That gives you 190. Now, this fifth postulate says, as you can see on this particular side, this angle 1 and 2 add up to 170, which is less than 2 right angles. What is the meaning of 2 right angles? 180 degrees, because 2 right angles means 2 times 90, that is 180. So since this is less than 180, sum of angle 1 and 2, so the lines will meet towards this side. The lines AB and CD will meet towards this side. Now you might say this look pretty obvious with the diagram, but yes, postulates are obvious truths, right? So when you try to extend these lines, you will be able to see that they will meet towards this side, but towards the other side it will keep on digressing more and more. You can see it met over there. Yes, but over here, if you keep extending, this will go on far and more far and far and far. Yes, that is what the fifth postulate says. If the sum is more than 180 degrees to that side, it won't intersect, but if the sum is less than 180, it will intersect. Now you can think, what if the sum is 180 degrees? Now that is an equivalent version of fifth postulate, which gives us the parallel lines. Now here we have a little bit of axiom which is based on the postulate number 1. Now it says, given two distinct points, there is always a unique line that passes through them. If you have two distinct points, suppose over here P and Q. So from P and Q, we can make infinitely many lines, right? As you can see, I have made around 10-15 lines. I can make more points which passes through P and Q. But there will be only one line over here. You can see the line L. Oh, sorry. Over here, as you can see the line L, only there is one possible line which can pass through both the points P and Q. That is how Axiom 5.1 says, given two distinct points, there is a unique line that passes through them. I hope that is very, very much clear for you. Now, once we have understood the axioms and postulates, there is something called as theorems and propositions in mathematics. Now, as I discussed already, theorems, axioms and postulates are obvious truth. We take something as a truth, and then we build on something, build on the other concepts of mathematics. Those are called as theorems and proposition. Theorems or proposition, statements or results which can be proved using axioms and postulates. Those are called as theorems and propositions. So in mathematics, we generally have axioms, theorems, and postulate. There are some more things which, as we progress, there are something called as converse of a theorem. There is something called as corollary of a theorem. As we progress in these videos, we will try to discuss all those aspects. Yes, let's quickly go through one example of how do we use these postulates and axioms. So example number one says, if A, B, C are 3 points on a line, as you can see, this is over here we have line L, and there are 3 points A, B, A, C, and B lies between A and C. So A and C are the points, and B lies somewhere between them. Then prove that AB plus BC equals AC. AB plus BC equals AC. Now this also seems very obvious kind of thing, but how will you prove it? With the help of axioms, right? What does axiom says? Quickly, you can go through the third and fourth axiom. With the help of that, you will be able to prove it, which says that if you add the equals, the resultant will also be equal. Yes. So as you can see, when you add AB and BC, you will get AC. Because after adding, you are getting it as AC. Now, you can also try to use the overlapping overlapping axiom, where we discuss that things which coincide each other are equal. So you can bring in the line AB, you can bring in the line BC, and when you observe AB and BC is overlapping or coinciding each other, that according to that axiom we can say that AB plus BC equals AC. I hope that makes sense. You can use both the axiom, but I'm very much sure the second thing which I told, the coinciding one, that makes more sense. You can use any of those. Let's discuss one more example. Example number 2 over here. Prove that an equilateral triangle can be constructed on any given line segment. Okay. So for that we will be needing a compass. Now, what we will do is we have a line segment AB. Now that this statement says that any given line segment, which we can draw a equal, equilateral triangle. Now, what is the specialization of equilateral triangle? That all of its sides are equal. So what will I do is I will take a compass, take the center of the arc as A and radius as the length AB, and draw an arc. The same thing I will do with the same thing I'll do with I will put the take the center as B, and now BA as the center, obviously BA equals to AC, and then draw one arc once again. Now what will I do? I will connect these points. Wait. Just a moment. I will connect this A to this intersection point, and then once again this A to intersection. Now this, if we name it as C, this triangle which is formed, the triangle ABC, it is an equilateral triangle. But how do we understand that it is an equilateral triangle? I will first verify that and then tell you the reason according to the axioms. As you can see, the AB has a length of around 4.5 centimeter. Yes. Now let's quickly try to measure the length of AC. This is also 4.5. Let's quickly try to measure the distance of BC. This is also, you can see, around 4 centimeter, 4.5 centimeters. So we have verified that with the help of scale. But let's try to understand it. More mathematical thinking we will try to apply. Now AB suppose has a centimeter. Suppose A is just a variable I'm taking. AB is a centimeter. Now, when we took A as the center and AB as the radius, that means the radius is AB, right? And this is the arc we drew. Now, the C is a point which is on the arc, yes or no? That means I am connecting a point on the circle. Obviously, arc is a part of circle. On the a point on the circle and the center. A is the center, right? That means AC is also AC is also the radius. That means it will also be a centimeter. Now what did we do? We took B as the center and BA as the radius. That means it's again a centimeter. And then we made a circle. And again, as you can see, this point C is meeting this circle. So this the point on the circle connected with the center, that gives you a radius, and radius is a centimeter. So this is also becomes a centimeter. That is how we can understand that. Now, whatever reasoning I gave you to explain this, this all involves the axioms. Now, we have become so used to those axioms that you might not have been able to see those axioms. You can go back, just try to understand which axioms did I use while proving this result. Okay. No, now in this particular chapter, whenever the proving comes, you just have to write the theory part. No need to draw or anything like that. Just write the axioms whatever you are using. No need to write the axiom number. Just write the name of the axiom, the sentence. Obviously they're pretty obvious, so you need not memorize it also. Yes. Now whatever axioms you identified I used to prove this, just comment down. I will try to I'll take a look obviously, and then we can have a very good discussion on that. Now with this, as I defined what is a theorem, it's a statement which can be proved with the help of the axioms and postulate. Let's understand the theorem 5.1. Two distinct lines cannot have more than one point in common. I repeat, two distinct lines cannot have more than one point in common. Two distinct lines. Two distinct lines. In this scenario, does these two lines has a common point? No, right? Because they are not intersecting till now. When they will intersect, they will have a common point. As now you can see, now they are intersecting. Yes or no? So are they intersecting at more than one point? Obviously not, right? So they are only intersecting at one point, and that is why the theorem that it cannot have more than one point in common. Yes. Now you might be thinking, this is a theorem, how to prove this? This can be proved using one of the axioms, which says the axiom 5.1. Quickly go through this. What does it say? Given two distinct points, there is one unique line that passes through them. Think about this and try to come up with a proof. Write down in the comment section. If you are not able to give the proof, I will give you the proof in the next video. Just comment down if you're not able to understand the proof. But you have to use theorem axiom 5.1, or you can use the postulates as well, postulates and axioms, which we discussed initially of the video. Now, one more equivalent version of Euclid's fifth postulate. This I will discuss in detail. Now, for it says for every line L and for every point P not lying on L, there exists a unique line M that is passing through P and which is parallel to L. What does it say? If you have a line and you pick a point P which is not on this line, I will try to explain it with the figure. I have the line L and I take a point P which is not obviously not on this line L. Clear? Now, what does this equivalent version says? That no matter how many lines you make from P, there will be obviously infinitely many. There is only one possible line, or you can also say always there will be a possibility of one line M which will be parallel to L. And it will be only one possible line. There will not be more than one possible line which is passing through P and it is parallel to L also. Yes, that is what it says. Now, how is it related to Euclid's fifth postulate? Let's quickly revise what is Euclid's fifth postulate. What does it say? Angles on the same side of transversal, if it is less than 180 degrees, it will intersect on the same side. Over here, now the condition, the obvious thought process of obvious question of Euclid's fifth postulate is, what if it is 180 degrees? It will never intersect and it will have equal distance throughout, and that is what this particular statements tells us that. Okay, there is one more subsidiary statement to that. Two distinct intersecting lines cannot be parallel to the same line. What is the meaning of that? Let's quickly understand that. Two distinct intersecting lines. Two distinct intersecting lines. Now these both lines cannot be parallel to the same line. For example, if I draw one line like this, okay, I will name it, so it will be, I had L and M, so they are intersecting. Now what does it say? These both lines cannot be parallel to the same line. So I draw a line N which is parallel to N. Can you say that it is also parallel to L? We can never say that, right? Because after some time it will intersect L. L will intersect N. Similarly, if I draw one line which is parallel to L, which is parallel to L, okay, I'll name it as O. Line O is parallel to O. Line L is parallel to M. Sorry. Now, as you can see, it is intersecting M. It is intersecting N as well. So that is what this particular theorem or this particular equivalent version say. Two distinct intersecting lines cannot be parallel to the same lines. This is also a subsidiary statement to that. I hope this particular thing make much sense to you. Now, there is one example once again. Consider the following statement. There exists a pair of straight lines that are everywhere equidistant from one another. That are everywhere equidistant from one another. So, it says that every time we can find a pair of lines, if you find the distance between them, it will always be the same. Now, let's try to use the scale and try to find the distance. Now, if I keep the scale like this, can I say the distance between these two lines is 3 centimeters? Absolutely not. So always understand that whenever we are finding a distance, we keep the scale perpendicular to the two lines. Okay, so now as you can see, it is 2.2 centimeter. As you progress on this particular line, this distance is kept constant. This distance is not moving at all. No matter wherever I take this scale to, this distance remains the same. And that is what this particular statement says. Okay, there exists a pair of straight lines that are everywhere equidistant from one another. That means if you find the distance from L to line M, it will be same throughout. So is that statement a direct consequence of Euclid's fifth postulate? Yes, obviously it's a direct consequence. What is the meaning of direct consequences? Now Euclid's fifth postulate says on the same side of transversal, if it is less than 180, it will meet on that side, right? It will intersect on that side. Over here, it's very clearly visible that since that distance is the same, the transversal which we will make over here, the transversal which is making a 90-degree angle, that means it is almost giving us the distance. This will give you 180 degrees and those lines will be parallel. Okay, that is how it is equivalent to the fifth postulate. If you have any different reason, you can also try to give that. There are several answers possible to this. This is one of the answers which I gave you. Yes. So now whatever we discussed in this chapter and the chapter in the lines and angles, triangles, whatever we are going to discuss next, we will be only focusing on Euclidean geometry. However, the axioms and theorems which we will be using over there, it will be slightly different from Euclidean geometry. I mean, what the axioms and theorems what we have discussed. Now, that slight difference is for us to understand in our terminologies. Okay, that is why. Now, that is one such thing. Now, if I'm telling Euclidean geometry, now does something exist which is non-Euclidean as well? Absolutely yes. As I mentioned already, that whatever we are discussing in geometry right now, it always have a straight line. Now, what if we don't have a straight line? We have curved lines. Yeah. What if we have circular lines, spherical objects? So those things are comes under spherical geometry, and that geometry is also known as non-Euclidean geometry. Whatever theorems, whatever proofs we have in Euclidean geometry, that does not work in non-Euclidean geometry, because over in non-Euclidean geometry, even a triangle can have more than 180 degrees as a sum. Okay, so yeah, with this example itself, you can see non-Euclidean geometry is a completely different branch which we will be not studying right now. We will only focus on the polygons or the geometry related to straight lines. I hope you learned most of the topics of this particular chapter. Thank you so much for your patience hearing. I hope you enjoyed this particular session, this particular Euclid's geometry chapter. With this, we end this chapter. Now, for this chapter, I cannot bring out some problem solving. For other chapters, I'm bringing a problem solving video as well. For this chapter, I don't think it is required, but if you think you need some of the proofs which I just verbally explained, you want me to tell how to write those proofs, I'll obviously make one video. You can just put your comments down so that I can get to know that you need those videos. Thank you so much for your patience listening and being with me on this journey of a little journey of Euclid's geometry. Thank you so much. You were watching Apna Gurukul Maths, one little step towards success. Thank you so much. We will see you in the next video with a new chapter or problem solving session. Until then, keep smiling. Jai Hind.